Everyone, welcome back to µCast. Today we're talking LEDs, which are all the rage right now. We got them in flashlights, we got them in your house lights. People have lost their crap over LEDs. Most people don't even know what LED stands for. So, what we're going to do, first of all, what does it stand for? Light emitting diode. Don't worry too much about what the diode part of it means. It emits light. It's a light emitting diode. So let's demystify these a little bit and talk about them. People have questions about how they work, why they're different from regular lights. So we'll cover some of those things today. So let's first come down here and take a look. This is a traditional incandescent bulb. You apply a voltage to it and it'll light up just like your old style light bulbs. And then we've got here some LEDs. We got small ones, they come in a little bit bigger. Different colors, as you can see here. I've got a board here where I'll just point to it with my pencil here. Right here, these four things are all LEDs, different colors. So they come in very small packages and bigger packages. When we're dealing with electronics, we're not going to deal with incandescent bulbs a lot because while they can work at lower voltages, they suck a lot of power, create a lot of heat. LEDs are nice that way. Not that they can't create heat, the higher power ones will. But generally they're cool to the touch. You can touch them, no problem. They light well and they don't take a lot of power to run. That's why for battery powered applications, if you've ever noticed your LED flashlight, you can leave on for a couple hours and it'll still be okay. Whereas your old one that has just the incandescent bulb in it, that thing's dead in like 25 minutes if you just leave it on the floor. Anybody that's got kids, you know what I'm talking about. LED flashlights, saving us some money. Okay, so this is the schematic symbol for an LED. Now we haven't talked about diodes, but a diode is the exact same thing without the little lines. The lines mean light. So anyway, that's the schematic for it. It is important which side the light is on here because through a diode, current can only flow in one direction. That is this way. Current will not flow backwards through a diode. Diodes are used a lot of times in circuitry for protection. So in case you hook your batteries up the wrong way in a toy, a good toy will have a protection diode in there to prevent current from flowing the wrong way through it and blowing it up. It'll have what's called a protection diode. So a light emitting diode is just that, it's a diode, but we won't get into the physics of how these works. If you want to learn more about that, check it out online. But anyway, when current passes through it, things happen and light is emitted. And so this is a graphic of it. Now you notice on these, there's a shorter leg and a longer leg to help you distinguish which side is the positive and the negative so that you don't hook it up backward. Now there's a couple of different ways to distinguish that. LEDs will have, a lot of times these kinds right here, will have a flat side. That is the negative side, or the cathode. The positive side is called the anode, the negative side is called the cathode. Don't worry about that, you don't have to remember that. Just remember, these need to be hooked up a certain way. If you forget how to tell, just look it up online. No big deal. Don't hook it up backwards, bad things will happen. You're going to ruin it. So anyway, the other way that you can tell, so you can tell by the leg length, there's a flat side on the cathode side, on the negative side, and then if you can look inside of these real close, you'll see that there's a bigger chunk and a smaller chunk. The bigger piece is on the cathode side, will be negative. Those are different ways that you can tell how to hook these up. Now for the smaller ones that I showed you down here on the board, those have an indicator on the bottom, you have to look at them real close, helps to have a magnifying glass. But anyway, these need to be hooked up a certain way. So let's play with one. Let's light it up. So the first thing I want to do is come down here to our breadboard. And I've got the same setup that we've been using in some of the other episodes. I got a 9-volt here. And what I'm going to do is I'm going to connect the negative side to ground. And I'm just going to leave the positive side out there. And then what I'm going to do is take the positive, put it in here, and then I'm going to complete the circuit. So current's going to flow out of the positive through the LED back to negative. It completes the circuit. Let's see what happens here. Okay, and if you caught that, it lit up for just a second and then it went out. What happened? This LED is dead. Okay, so we saw when we hooked the LED straight up to a battery, too much current flows through it, lights up for a second, burns out. So what do we need to do? We need to resist the current some. We need to put a resistor in. So let's draw our schematic here. We've got our battery. Don't leave the symbols freak you out. This is easy. You guys can handle this. No problem. We want to put a resistor in and then go through our LED. Okay, we know this is 9 volts. We need to figure out how to limit the current going through the LED by putting a resistor in there. Well, we had an episode on Ohm's law, so we know the magic formula, V equals IR. That's all we need to know to figure out what kind of a resistor we need to put into this thing. So the first thing that we need to know is how much current is too much current. Well, on an LED like this, 20 milliamps is normally what you want to keep it under. So for our I, 20 milliamps. Now we don't want to push it all the way to the limit, so let's go something a little under. There's no exact science to this. I'm just giving myself a little bit of a buffer. Let's say 18 milliamps. That's under 20. We should be good there. Now we need to figure out R. That's what we're trying to solve for here. Now, your first instinct might be to say, oh, I know V, that's 9 volts. That's where Ohm's law gets a little tricky. It's not always just the battery that you're using. You need to know what the voltage is across this resistor. And that brings up an important properties of LEDs, which is a forward voltage drop. We know that we've got 9 volts from here to here, which, if we just slide over, means we have to have 9 volts from here to here. Well, in the data sheet for your LED, there's a property called the forward voltage drop. That is going to, in a very simplified terms, if anybody super technical that knows about this is watching, don't give me a hard time. We're going to say that the LED uses up 3 volts. I know that's not entirely accurate, but we'll say it's 3 volts here. Which leaves, just by the math, these have to add up to 9, that leaves 6. 6 volts is what should be across this resistor. Now, this isn't an exact science. If you look in the data sheet, it'll have a minimum, it'll have a maximum for forward voltage, it'll have a typical value. Just use the typical. We don't need the resistance to be a precise value. We just need to keep the current under control. That's all we're trying to do. Don't let some of these things freak you out and think it's more complicated than it is. This is really easy. You guys can figure this out. So 6 volts is really what we want to plug into our equation here. 6 volts. And then this is times R. All we need to do is solve for R, and we should have the value that we need to put in here. So what we do is we have R, I'm just going to move the R to the other, flip this equation around, is equal to 6 volts over 18 milliamps. Important thing to remember about Ohm's law. The V is in volts, the I is in amps, the R is in ohms. Well, we're dealing with milliamps. We need to go back, like we talked about in the units episode, and we need to take milliamps and turn it into amps. That's very simple. All we do, if you look at one of those sheets that you downloaded as a reference, you just have to slide the decimal point 3 places over. 1, 2, 3. Fill in a 0 there, so what we really get is 6 over 0.018 amps. Same as 18 milliamps. That will give us the value of our resistor. So if we take that, just grab a calculator here real quick, and we'll do 6 divided by 0.018. We're going to get around 333.3. You're not going to have a 0.3 resistor. So we're about 333 ohms. If we put a 333 ohm resistor in there, we should be somewhere in the ballpark of 18 amps like we wanted to be. So I just so happen to have a resistor that meets those specs. So let's come down here to our circuit here. Now we're going to hook the resistor up to the positive, out to our breadboard here, and just to prove that we're not doing any hand waving, Remember, we know how to read these resistors because we watched the resistor episode. We're about 323 ohms, so we're pretty close to that 333. Remember, this is not an exact thing. We don't need to meet exact numbers. Don't worry about, it's off by a few ohms. We're just trying to be in the ballpark. Alright, we'll hook up the supply here. And now I'm going to use my meter to complete the circuit. If you remember from the multimeter episode, we want to put this in line to measure the current and see how much current is going to flow through our little circuit here. So I'll put that there. I'll put that there. It'll light up. And you'll see there we're right about 17.65 milliamps. We're just under 18 there. That's it. That's all there is to LEDs. Very simple. We got this in our tool belt. We used Ohm's law to figure out the value of R to put in there to limit our current. That's all you need to know about LEDs for now. Don't hook them up backwards. Don't put too much current through them. And have fun with them. Hook some up. If you blow one up, it was 99 cents. Buy another one. Not a big deal. Just have some fun with them. If you have any questions, something wasn't clear, comments below. Otherwise, we'll see you next time. Peace it out.